Thanks very much for the introduction, and thanks very much for having me. I enjoy very much being here. Thanks to the organizers for putting together this nice little conference on quantum reconstructions, which I'm not an expert in, but I'm very looking forward to learn more about the program. So Philipp talked about it a little bit in the beginning in his introduction, where he mentioned some of the basic principles, and so I'm not going down all the way down to this reconstruction program, but I will do something different, but still similar, which is I will not assume that quantum theory, I will not agree on, I will not assume the quantum formalism, but I will still assume that the experimental or empirical export of the theory is correct. So I will assume that the quantum probabilities are there and they are describing the world correctly, but I don't want to assume any of the formalism. You also mentioned Zeiling a bit, and that reminded me of a very brief discussion I had the pleasure to have with him. And he shared a sentiment with me, which was on discussion about what it would mean that information is fundamentally said. Maybe it's quantum randomness that is a fundamental feature of the world. And so this is going a little bit in this direction, because I will try to argue that if we deviate from the quantum probabilities, then some things go wrong with contradicting first principles. Okay, but I want to start with a classical example where, okay, here you go, where it's clear what's going on. So imagine we have a classical physical system, a gas in a box that is described by some state variables, pressure, temperature, and volume. So we're assuming classical thermodynamics. And there's an ensemble of systems, an ensemble of particles. And this gas in a box is described by this theory macroscopically. So we have some state variables that fix the overall state of that system. And we perform measurements. Every now and then we let out a particle and measure its velocity. And from this we recover a probability distribution of velocities. For example, it could be the Maxwell-Boltzmann distribution. So every time we measure, we get a different velocity and we recover some statistics that might be predicted by the thermodynamic state of the system. Okay, well, as you saw, there were two dips here. There's two peaks, and that's not coincidental. It actually turns out that the observer discovers that the gas in the box is not just air, but it's a mix of nitrogen and oxygen. So the observer has discovered that there is more to the system that she didn't know about, which she can use to separate out into sub-ensembles and to make a better prediction of what the outcomes of these measurements are. So on average, if we average over these two sub-ensembles here, we still get the same distribution, but the observer is now assumed to be able to measure if it's nitrogen or oxygen, and conditioned on that new knowledge, she can now make better predictions. Okay, so on average, it complies with the theory, but she discovered new variables that she can, in fact, operationally control to make better predictions. And so you can see where this is going. The question now is if quantum theory could be subject to the same thing. Is it possible that we have missed some variables which can be used to improve the predictions of quantum theory? So the question is whether quantum theory is predictively complete. Okay. Why do we say that quantum theory is a probabilistic theory? Here's a very, very simple way to see this. So assume that there is a target system and an environment, and there are measurements performed on the target system that are represented by the POVM EX with outcomes X. And then there's measurements performed on the environment with POVM EY and outcomes Y. And assume there is the total system is described by a generic quantum state, which you can see on the top, and assume that the target system is described by a pure state. Then it very straightforwardly follows that the two systems decorrelate, which is to say that the probabilities of the total outcomes are going to factorize. So the environmental degrees of freedom are independent of the degrees of freedom of the target system. And so if we assign a pure state to a system, then we already know quantum mechanics predicts that there's nothing in the environment upon which I can conditionalize to make better predictions than what I have from the wave function. So the wave function in that sense encodes all the knowledge I can have about the outcomes of experiments. And so if it was possible that there are additional variables, that it would have to break this quantum decorrelation principle. Okay. Of course, I'm not the first one to ask this question and study this problem. It basically started with the EPR paradox, or the EPR paper, where they asked, can a quantum mechanical description of physical reality be considered complete? And of course, the argument was that if entangled states do exist, and here's the basic setup of the EPR experiment, I have a source that sends out a pair of particles, and I have two observers that measure each particle, and we have these strong quantum correlations due to entanglement. And if the quantum state were in fact complete, but it's still the case that one observer can predict with certainty upon measurement what the outcome of the other observer is, then according to EPR, this is some way to break locality. So this is EPR non-locality, because one observer, if the wave function is complete and it's not predetermined what the outcomes are, but one observer can still determine what the outcome of the other one is, then this is EPR non-locality. And so they thought it should be an incomplete theory. There should be more variables to underpin the theory that do predetermine the outcomes of the measurements. But I'm not concerned with this sort of completeness, because EPR were mainly concerned with ontological completeness. They didn't want to say that quantum mechanics is predictively wrong or something like this. They just wanted to say there should be additional variables that predetermine the outcomes to avoid this spooky action at a distance. And of course, a very strong opponent was Niels Bohr, who thought that the wave function isn't doing anything like this. It doesn't describe reality at all. So if you are in the camp of Bohr, this question might not be interesting. If you think that the wave function is the only tool that we can and have to use to make predictions about the world, this problem might not be interesting. But if we are not married to this idea, then you might still find it interesting to figure out what can we say from just the empirical predictions of quantum mechanics, if it's possible, that is predictively incomplete or complete. Okay, so why do I think this question is interesting? It's first of all, so based on what I said before, it's unclear what all the variables really are that determine the outcome of a measurement. If we assume the quantum theory to be correct, and at least when it comes to making predictions, then it's rather ad hoc to assume that the wave function would be the only thing that determines an outcome. And so it would be interesting to see whether it leads to any contradiction to introduce more variables that give rise to better predictions. And the other one would be to have a better understanding of quantum indeterminacy motivated by first principles. So maybe we can find some principles that would be violated if we had predictive advantage over quantum theory, and then use these as motivations to say that, to argue for the fact that quantum uncertainty is in some sense fundamental. And that's what I'm trying to do here. I'll make a couple of assumptions from which I think this claim can be made. And this is what I will do now. But before, I want to make a precise definition of what I mean by saying that a theory is empirically complete. So imagine we have two theories, two competitive theories. One makes better predictions than the other. And the way in which we do that is that both agree on the preparation. So we have a couple of variables here, y1 and y2. Both agree on the preparation y1, so there's some experimental procedure that prepares a state. But theory 2 says that there is additional variables y2 that could also be used to condition your outcomes on. So on average, both theories give the same probability distribution, but theory 2 has now additional variables. So when we condition on them, gives a more precise prediction. So it's a non-trivial empirical extension of the theory T1 if there exists at least one variable y1 for which the probability px of there exists at least one variable y2, for which the prediction p of x given this variable deviates from p of x given y1. Okay, so this is just basically saying, in the case of the gas, the theory 2 would say, okay, there's actually nitrogen and oxygen that's in the box, and if you know which gas you're dealing with, you can predict more accurately what the velocity distribution will be. And theory T1 will say, okay, I just know about the pressure, temperature, and volume, and I don't know that there's more microscopic degrees of freedom, and I can just predict the Maxwell-Boltzmann distribution less accurately than what the other observer can do. Okay, now there's the question to what these variables really mean. We need to make a bit more sense about the outcomes x and the preparation variables y1 and y2. This actually goes back to a question that I asked earlier about where do the measurement outcomes live. So I want to make I want to make an assumption about this. So I'm assuming that there is some manifest domain to which observers have access to that can be operationally controlled and manipulated in the laboratory. And one example is that you assume it's going to be manifest configurations in 3 or 4 dimensional space, let's say. And so the manifest domain could be something like this, and then a prediction would be to use a subset of these position degrees of freedom and assign a probability distribution to a later slice of that manifest domain. Okay. So I'm not claiming that this is the way in which we should do it. I'm just claiming that there has to be an assumption about what the variables are that observers can access and manipulate. Because these will be the observables that can be used to base your prediction on. Right? And there might be other variables. Maybe there's an ontological domain where the manifest configurations signify the preparation of some ontic state or something like this. But I want to stay away from assuming the existence of that. You can add that if you want. So for example, a preparation y, so y can be some of the dots here, for example. A preparation y corresponds to a non-unique preparation of some ontic states, lambda mu q of the measurement device and the target system. But that's not really relevant. I just want to make sure that there is a distinction between the two domains, and it's important that we agree on that there is a set of variables to which the observers have access to. Otherwise, it gets complicated. If we don't have this distinction, then it's not clear what a prediction really is and what the limits could be of an observer to predict things. So let's say that the world is fundamentally deterministic, and you just add enough information into the initial state that makes the world deterministic. Then, if we don't make an assumption to what variables are accessible, observers could make deterministic predictions as well. And incidentally, it's always possible to introduce a deterministic underpinning of a probabilistic theory. As I said, you can just add enough information in the initial state and it will be deterministic. So there will be some principles that need to rule that out. Okay. So now to the basic setup. I will now introduce the basic assumptions that I will make and then the main claim. And after that, explain a bit more about what the role of non-locality is here. So I've got 3 observers. There's Alice and Bob. Alice and Bob share an entangled pair of particles. And there's a third observer, Maggie, that possesses what I call a magic prediction box that spits out variable Z. And upon conditioning on this additional variable, she can make improved predictions on what Alice would predict about the outcomes X. So we have an entangled state that is assigned to Alice and Bob. They have measurement settings A and B, and the outcomes are assumed to be binary, 1 and 0, X and Y. And then there is this additional observer, Maggie, who can condition the prediction of Alice based on the variable Z, and thus have predictive advantage over that. So all of them know what the quantum state is, but Alice and Bob don't have access to the additional variable set. Only Maggie has access to this at this point. So this is the basic setup. And the first assumption is what I tried to allude to before. It's the assumption that there is some domain to which observers have access to. So there exists a domain of manifest variables, operationally accessible, based on which all state preparations and predictions supervene on. So this is, in a sense, saying that there are no hidden variables in the usual sense, because, for example, if it was possible that Z does, in fact, improve the predictions, then that could be seen as a hidden variable. But I'm assuming here that Z is an outcome of a measurement, so Maggie has access to actual outcomes, which signify the preparation of Z. So this is not a hidden variable in the usual sense. This is the first assumption.
Can I just ask quickly, what does Maggie measure on? Is that the part A of the system?
So I'm not really assuming that Maggie chooses a setting and performs a measurement. You can think of it as something like every time the source spits out a pair of particles, Maggie reads some pointer configuration, and then she can make a prediction based on the pointer configuration and the total state. She also knows the total state. So there's some device in the lab that tries to tell you more about the outcome of measurements than just the quantum state. And I'm not making any assumption on how this is realized and what the dynamics of that is. Okay, so the next assumption is we have a predictive advantage, which means that the quantum probabilities decompose into finer grained probabilities. So these are the predictions of quantum theory on the total state if Alice and Bob measure with the POVMs EA and EB. And to have a predictive advantage, as I introduced before, is to have a decomposition of these probabilities based on which, if I condition on Z, I get a finer prediction. And I'm assuming that there is at least one single prediction that is better than quantum theory. So it's a very general assumption. I'm not assuming that some particular predictions that are refined. So I'm assuming that there's at least just one single prediction for which Maggie can have predictive advantage, and we will see that even if you assume that it cannot go, it cannot be possible. Okay, then the third assumption is one on the relationship between Maggie and the other observers, and I call it reliable intersubjectivity. So I haven't said anything so far what the relationship between the observed values set and the settings of Alice and Bob and their outcomes are. Because it could well be that the outcome of Maggie is indexed by the observer. Maybe it's a relative outcome, such as in relational quantum mechanics or cubism or Everett. So we need to make an assumption about the relationship between the observers and the outcomes, and let's assume that all the observed records have well-defined values for all observers. So if there's a value set, then all of the observers can agree on the same value. And on top of that, I also assume that this value set can be reliably reported to Alice. So Alice and Sadie can talk to each other, Maggie can talk to each other, and if Maggie observes a certain outcome set, and she reports it to Alice, it's going to be the same outcome. Because you can imagine that upon interaction of the two observers, the value is disturbed. Yeah. And we will see that in some interpretations of quantum mechanics, this is in fact the case. Okay. Last important assumption, and then there's one more auxiliary assumption. So based on the assumptions I made before, we can write down an objective probability distribution, because now all the observers agree on the variables. And since Z is accessible and controllable, it means that if it's possible that I could change the outcome of that Alice could change the outcome of Bob by choosing a measurement setting conditioned on Z, this is not just a parameter independence, this is signal locality. So I'm making this is the locality assumption that I'm making here, that Alice and Bob cannot signal even if they know the variable Z. Okay. So in a hidden variable approach, if Z is inaccessible, like in pilot wave theory, where we have particle configurations, this would be parameter independence. But I'm not assuming this. There could still be a lot of variables on the microscopic level that communicate non-locally. There's not a problem with this. Just saying that all the things that are accessible, all the variables that are accessible by the observers, they have to be local. So I'm not ruling out any interpretation with this assumption. And there's one last assumption that we need for the main claim, which is that the variable Z is independent of the measurement settings too. And in the literature, that's often referred to as no conspiracy or no superdeterminism. Okay. Now, if we combine all these assumptions, we get a contradiction. And as a result, one of the assumptions has to be wrong. That's the main claim. And the way to do this is to use non-locality. And what we need for this is a more generalized version of non-locality. And for this result, I draw on the generalized chain Bell inequalities that were first introduced by Brownstein and Caves. And you can see my version of the definition here. So we sum up all the differences of the measurement outcomes and average over them. And it turns out that if the theory is local, there's a local hidden variable theory that explains these statistics, then it would have to be greater or equal than 1. And it's also the case that in the setting where we have the Bell experiments, so 2 settings on each side, we get that this IN reduces to the CH-SH inequality. So in that sense, it's a generalization of the standard Bell inequalities. Okay, and with this definition, we can now study these alternative probability distributions that include the additional variable Z, and we can see if we run into any contradiction with quantum theory now. Okay, so I'm assuming that the state of the total system is an entangled state of this form. I parameterize the entanglement with this vector alpha. And on the right-hand side, I've worked out the value for IN for this state. And you can see there's a term that only depends on the differences of the measurement settings. And then there's an extra term that scales according to alpha. This will be important in a minute. In the case where alpha is 0, we only have the first term. And it turns out that this tends to 0 in the case where I have an unlimited number of measurements. In the case where I have a non-maximal entangled state, I cannot get rid of the second term. This will be relevant in a second. Okay, now the crucial insight was, this goes back to Barrett and others, you can relate the value IN to the difference of the predictions so if we translate this to my measurement setting, then you can relate the value IN to the difference of the predictions that Maggie makes. So assume for the sake of this argument, that we have a maximum entangled state, then the predictions would be 1/2 probability for all the outcomes. And Alice's prediction, or Maggie's prediction here, if Maggie has a predictive advantage, then it should deviate from the prediction 1/2, which means that the difference between these two outcomes, or the difference between the probabilities of these two outcomes, would have to deviate as well. So in this case, that's what it means to have predictive advantage, that Maggie doesn't make a 1/2 prediction for the measurement outcomes of Alice, but it's something that deviates from the equiprobable prediction. And so we can relate the value in to this. And for maximum entangled states, as I just said, we have that this difference is non-zero. And by definition, we also have that on average, the predictively advantageous theory has to recover the quantum probabilities. We get that we can rewrite this as an average over these differences, and they will have to be smaller or equal than the quantum value. Because on average, we need to reproduce quantum probabilities, and we learned that we can relate the generalized Bell inequality to the predictions of Maggie. And now it turns out for a certain choice of measurement settings, if I choose equally distribute the measurement settings on the Bloch sphere for both Alice and Bob, then it turns out that this value tends to 0. So for every epsilon I have here, if I assume there's predictive advantage, there exists a measurement scenario with n measurement settings such that the quantum value is smaller than this epsilon. Okay? And this in turn means that the difference between these two probabilities has to vanish. So as a result, Maggie cannot have predictive advantage. She has to, if she's subject to signal locality and reliable intersubjectivity, then she has to make the prediction 1/2, otherwise we would be able to signal with that. Okay, what about non-maximum entangled states? As I mentioned before, this first term vanishes for maximum entangled states, but for non-maximum entangled states, it turns out that we cannot choose a measurement setting for which this value vanishes. And so we would have to minimize over different measurement settings or different numbers of measurement settings, and there it turns out that it doesn't work. So in the case of non-maximum entangled states, one can actually write down a theory that has predictive advantage. And this was done, for example, by Chihardi and Romano in their paper, where they explicitly write down a hidden variable model for which one part is non-local and one part is local, and they show that it only works in the case of non-maximum entangled states. Okay. Now I want to say a little bit more about how to understand signal locality in the context of this claim. So we go back to the Bell experiment. We have the quantum predictions for an entangled state. We have two observers. And one step towards the result can be seen as the following. So assume that we have a deterministic prediction of the outcomes of measurements. That would mean that we have an empirical extension that is not only better than quantum theory, but it's deterministic for all individual outcomes. That's, for example, the case in pilot wave theory, because the total initial state fixes all the outcomes deterministically. If that's the case, then I can rewrite the total probability distribution, P, X, Y, given A, B, and Z. Because it's deterministic, it's just delta functions. So the outcome probabilities are just 0 and 1. I can rewrite it as a product like this, and you will recognize that this is outcome independence in the context of the Bell theorem. And if we, on top of that, assume signal locality, then the probability distribution fully factorizes, and we get the parameter independence here as well. So, and since we know that such a theory cannot reproduce all quantum predictions, it's ruled out by Bell's theorem that all of the predictions of quantum theory could be deterministic. But it doesn't mean that some of them could be still predictively better and indeterministic. So that was the more general assumption that I made which was predictive advantage, means there's at least one prediction that is better, but it doesn't have to be deterministic. So this result that goes back to Asin, Shisa, and Masan shows that we cannot have a fully deterministic empirical extension. But it doesn't show that we can have a partly deterministic empirical extension. And I want to mention also pilot wave theory again, because here one can very clearly see what's going on and how what locality plays a role of here. So assume pilot wave theory was true. So we have initial particle configurations on top of the wave function. So the source sends a pair of particles, and depending on where the particles start out of, that determines the outcomes on both sides. So I've plotted a couple of trajectories, as you can see. And the theory is manifested on local, so the trajectory on one side is going to depend on the measurement setting of the other side. Okay? And assume we have some magic prediction box that tells me what the initial configuration is. So here you can see, depending on the initial configuration of both particles, what the outcome is going to be as a function of the measurement setting theta. So in the case of a maximum entangled state, the outcomes only depend on the difference of the measurement settings, and that's this angle theta here. For example, if the particle Q1 starts out here, and if the total position of the particle Q1 and Q2 is here, for example, then they are going to observe the outcome down. And if it's outside of the shaded area, the configuration, then they're going to observe up, down, and similarly for down, up, and up. And the size of this shaded area depends on the choice of the measurement angle. Okay? So you can already see the following. If it was possible to know the Bohmian configuration, so let's say we start out here and we know that configuration, we could now choose by changing the measurement angle what the outcome will be on the other side. And that will give rise to signaling, because we can remotely choose the setting to determine the measurement outcome of Bob. But this only works if I can access all the points here by choosing the measurement setting accordingly. So let's say it turns out that the prediction is such that I can only choose the measurement settings such that the shaded area varies from, let's say, here to here. Then outside of that shaded area, there will be configurations that are not affected by the choice of the measurement setting. And you could write down a theory which says, okay, for all the measurement settings that I cannot reach with varying theta, I make deterministic predictions, and for all others, I just make the quantum prediction. So you would have predictive advantage that is in part deterministic. But it turns out that in pilot wave theory, changing the measurement setting here makes this shaded area survey the whole quadrangle. And so for every Bohmian configuration, I will always find a measurement setting to violate the signal locality, in principle. Okay, and that's also the reason where you can see why it's important to have many measurement settings. If we just had 2 measurement settings, then maybe the shaded area would vary from here to here, and then there would be extra configurations that are not affected by the settings. And so that's the reason. So here it's more explicit because we have a microscopic dynamics in pilot wave theory, but that's basically the reason for why we need to use the chain Bell inequalities to include all the measurement settings for which we could potentially signal. Okay, I said that. Okay. And as a side note, also in Bohmian mechanics, it turns out that for both the maximally and non-maximally entangled state, all the Bohmian configurations are non-local. So in all cases, you can always find measurement settings that you could in principle use to signal. What's not clear, what's an open question, is whether you could find a probabilistic distribution of initial Bohmian configurations that is still local. So it only works if you really had access to the full configuration of the particles. Okay. Two last things. One is the question, what happens if we violate the assumption of reliable intersubjectivity? And as it turns out, this assumption is violated by most interpretations of quantum theory. And now the question is, okay, what does it mean? Do we have predictive advantage in some of the interpretations of quantum theory? Technically, in the way I presented it here, yes. But there's some more problems here that arise. So, for example, Everettian quantum mechanics, relational quantum mechanics, and cubism, they violate intersubjectivity because the outcomes are relative to the observer. So the value that Maggie observes, Z, might be not absolute, and Alice and Bob may think that indexed on their experience that is a different value. And for example, in pilot wave theory, it turns out that if Maggie had that additional knowledge of Z, which would be the Bohmian configuration, if she interacts with the other observers, the pointer record would be affected. So in a way, that's saying that in pilot wave theory, it's impossible. It's in fact possible that you can have this predictive advantage for accessing the variable set, but as soon as you try to communicate it to the outside world, your memory is going to be affected, and it's not a predictive advantage anymore because it's not a reliable record. Yeah. So the memory states are disturbed in this case. And there's another problem. It's not even possible that Maggie would be able to do statistics. She cannot access the variable set and then save it somewhere and then do many experiments and communicate it to the outside world to figure out what the dynamics would be of that measurement disturbance. You know, she could maybe try to find out a way in which her memory is precisely disturbed to still account for the fact that there might be some dynamics that could still be used to predict better the predictions of Alice. So Maggie is not even in a position to do empirical statistics to figure out what the dynamics could be. And this is also complies with what we have in pilot wave theory, because the guidance equation that tells you how the particles move is underdetermined. There are many different versions of pilot wave theory with different particle trajectories that all give rise to the same statistics. And this shows that it's impossible to ever figure out which of the laws is correct in that sense. Okay, so there will be an epistemic boundary between Maggie and Alice in order to comply with the quantum probabilities. So it's up to you whether you think that's a predictive advantage or not. I think if you don't have this absoluteness of the probability distribution, then I don't think it's really a predictive advantage. But of course, it's up to you to decide. Okay, some related results to conclude. There was an interesting result by Wiseman et al., where they tried to show that the absoluteness of observed events is impossible. And that assumption is akin to reliable undersubjectivity. And in the framework I introduced here, the assumption amounts to something like, okay, there's an objective probability distribution. So here again we have A and B. This is in reverse now, unfortunately. A and B as the outcomes of Alice and Bob. And there are some additional variables, C and D, that Charlie and, don't know what they use for D, Debbie, I think, Charlie and Debbie can access. And in the context of this claim, the absoluteness of observed events means that there is one measurement setting for which the set variable agrees with the outcome of Alice, if Alice checks the set variable. So in a sense, this is a special case of predictive advantage. And they show with a simpler inequality that has 3 measurement settings that this has to be impossible as well. So this is the way in which it relates to this result. Then Kolbeck and Renner's result on no extensions of quantum theory can have predictive power. There they try to go, so it's not first of all clear to me how they make sense of an empirical extension and if the claim goes through really, but it would be nice to see how this works out in the case of non-maximum entangled states, because there they claim that you can show a similar result using chained Bell inequalities for non-maximum entangled states as well. So far I've only said that it's possible for maximum entangled states. There's another problem with this claim because they are appending systems, and there's a nice paper by Ronnie Hermans where he shows that there's an additional assumption that comes in which goes right to the heart of non-disturbance, and it's not clear whether you can really append the systems in this way. And this is necessary in this claim because they need that to reduce the non-maximum entangled state to the maximum entangled state. So I'm not sure, but maybe it works out. And then there's another interesting result by Bruckner and others where they have a simplified version with two measurements, and they show that in some cases, so they basically implicitly make the assumptions that I make, but they show that in some cases that the friend's memory has to flip, which is the case where reliable intersubjectivity would be violated. Okay, so are quantum predictions empirically complete? I try to argue with this no-go claim that yes, it's the case for maximal entangled states. It's impossible that there exists an observer and can in principle find out about additional variables that we didn't see before to subselect ensembles and have predictive advantage. So in a way, this shows that quantum uncertainty is a fundamental limit to nature's predictability based on a locality assumption mainly. And if we violate the other assumption of reliable intersubjectivity, it seems to me that this is in a way analogous to Laplace's demon, where there exists a demon that has access to all the microscopic information of the universe and could make deterministic predictions, but there's some logical problem with that because the demon has to be outside of the universe to make the prediction. Otherwise, he cannot make deterministic predictions if it includes itself. So there's some self-reference going on. And in the sense, it's similar here because if we violate reliable intersubjectivity, then Maggie really has to be epistemically detached from the rest of the observers to make these predictions. And so it's not really of any help. Okay, thank you.
Thanks a lot, Johannes. Please feel free to ask your questions, share your comments.
Thank you. Have you thought about non-composite quantum systems?
I haven't.
So, I mean, if you have a Hilbert space which has a prime dimension, where you can't have entangled states, is there anything you could say? Because that's part of quantum mechanics as well, those types of systems. And it might be that maybe there it would be possible to have more predictive systems.
So you're saying there are cases where I cannot have entanglement and I couldn't apply this framework?
Yeah, if your system is not bipartite but monopartite.
Absolutely.
And if it's not spin 1/2, where we have a hidden variable model.
Yeah, it would be nice to see some generalizations of this. I want to add that there is another problem here, of course, which is all of this just makes sense if I have at least two observers that could employ signaling. Yeah. So in the case of individual states, there's not a result like this. Yeah. But one idea could be to maybe look at contextuality. So if you assume something like macroscopic contextuality, then you could maybe make sense of a claim like this for individual systems and perhaps also for the cases where you don't have entanglement.
Thanks, I enjoyed that. Just I certainly see the value in fleshing out the framework in the way that you have. I'm just wondering, it's a bit of a naive question, I guess, but in a sense, isn't it? Why is it surprising that quantum mechanics is predictably complete? Don't we already know that from Gleason's theorem, for instance?
Why would you say that?
Well, there's a theorem.
So I think that the Gleason theorem is not enough for that, I think. I mean, there might be a way to rephrase it to make it apply to this framework as well, but I don't think Gleason's theorem rules out that there are additional variables that could predetermine the outcomes of experiments more accurately. It shows that the probability law is of a certain kind if you include. I mean, it shows that all the probabilities of quantum mechanics you can write as the trace of some operator times an observable, but it doesn't per se exclude additional variables. So it doesn't rule out pilot wave theory, for example. And it's not a priori clear to me that unless you do this sophisticated argument with non-locality and chain Bell inequalities, in the case of pilot wave theory, for example, that you cannot access any of the initial configurations. I don't think that.
Yeah, no, I see that. I mean, I don't think Gleason's theorem is intended to rule out pilot wave theory. I don't think that's the point, right? I mean, but like, and I don't think this is not an objection. I think so. There's a sense in which you're doing something deeper than that, but in terms of the main result, I don't. It seems like I'm just wondering, like, if there's something added to Gleason's theorem or theorems of that sort.
So I think that there could be a version of what I'm doing here using Gleason's theorem. I'm not sure, but maybe. The reason for why I say that it's not so straightforward, and the reason for why I mention pilot wave theory here is because Gleason's theorem doesn't rule out pilot wave theory, but pilot wave theory is an example where you have deterministic predictions. It's not clear unless you use this machinery of chain Bell inequalities that you really cannot use them to make actual accessible improved predictions. So I think it's possible, but I think it needs a bit more work. Yeah.
So I was wondering, thanks for the talk, I was wondering what use does this notion of completeness have in your talk? I mean, I see that you established, like others have done before, that quantum mechanics is maximally predictive. Right? There is no extension that makes, more predictions than quantum mechanics. But I don't see how that can be interpreted as establishing predictive completeness. Right? Completeness has many senses, and I would have thought that as a consequence of Gödel's theorems, right, quantum mechanics cannot be predictably complete because there's always going to be, true predictions that quantum mechanics cannot actually make, right? Being an extension of elementary arithmetic that follows just as a corollary of quantum Gödel completeness phenomenon. So maybe you don't mean predictive completeness. I'm just wondering, maybe this is not a well-formed question.
Yeah, thanks for that question. So to me it's interesting for the following reason. If we think that the postulates of quantum theory are to some extent ad hoc, like I would like to see a result that tells me, okay, I know that I can only make predictions up to a given accuracy because of quantum theory. But why should I believe that this is the last word on what I can predict, So there's the question, is the world deterministic? And we can never know because you can have a probabilistic theory, it can always be extended to a deterministic theory. But the other question is, so this is more like APR, right? They were thinking about the ontological completeness of quantum theory. They were using non-locality to argue that it's not ontologically complete. So they were hoping for a completion that gets rid of the non-locality, but then Bell showed that even if you have a completion like this, it has to be non-local as well. So this is about the ontological completeness, but the other question is it predictively complete? And as long as we just start from the empirical export of quantum theory, I don't see why it should be. Okay? I want to see a result like this that tells me it's not. And it would be interesting, I mean, if it was possible to have an empirical completion, then you could make better predictions in the lab. And so I guess it is an important question to me, because it would be it's interesting. It's interesting in the sense that I want to know whether the quantum uncertainty is, in a sense, fundamental. You know, are there future theories that have less uncertainty in their predictions? And it seems like it's not the case if we live in a world where the quantum probabilities are approximately satisfied. Okay.
We have about 10 minutes, so if you have any thought, comments, just feel free to share it. It seems that there's no further thought, so let us applaud Johannes for the second time.